So hello dear, good morning, welcome back. So today we are going to discuss orientation, and with reference to that we'll try to see how a typical solution from Euler angle representation of orientation can be obtained. And with that, before wrapping up, we also should discuss about a very important alternative tool for orientation representation known as quaternion. It's very so stay tuned. And some of the lectures on quaternion, if you already are familiar with, you can skip. But the thing is, since same technology is used for computer graphics people, for game designer, and I think it will be good if we actually um, uh, discuss something about those tools. Okay. So before going further, just recapitulate, and today we are trying to discuss also some geometrical interpretation of orientation matrix or rotation matrix, because if you know geometrically what it is meaning, then sometimes apprehending rotation will be, I think, useful for understanding. Okay, so let us try to recapitulate. You know that the structure of the rotation matrix R is equals to Ix dot Iu row wise. Okay, then Ix dot Jv, Ix dot Kw. Then row wise Jy dot and you know what is Iu. I think this is already known to you. So this is my X, Y, Z, and this is also U, this is V, and say this is W, okay? And this is origin O they are sharing. And this is Ix means the unit vector along x-axis, Jy unit vector along y-axis, and Kz unit vector along z-axis, Kw actually unit vector along body coordinate z-axis of the body coordinate frame, Iu actually unit vector of x-axis of the body coordinate frame, and Jv actually unit vector along body coordinate y-axis of the body coordinate frame. Okay, so these are what they are represented here. So what you see first of all the determinant, and these are all unit vector, right? And determinant will be equals to 1 for right-handed coordinate system. Okay, and will be minus 1 for left-handed coordinate system, but more prominent one is right-handed coordinate system, so we should try to remember. And you can verify with any rotation, maybe about x-axis, some angle or whatever, right? Also, the inner product of each row with each other row will be 0. So this row dot product between the inner product with each row, okay, and this will be equal to 0. Same thing is for dot product between of each column with any other column will also be equals to 0. And I think the most important relation what you know is actually R inverse equal to R transpose, or this directly is giving you R transpose equals to unitary matrix. And also geometrically you see this is the dot product, right, of Iu, Jv, K, W with reference to the unit vector of the inertial coordinate frame. Okay, so each row represent that is the dot product of uh, uh, principal axis of the body coordinate frame with one axis, that is Ix of the inertial coordinate frame. Similarly, this is also dot product of that is the projection of the body coordinate frame with respect to uh, y-axis of the inertial coordinate frame, projection of the body coordinate frame with respect to actually z-axis of the inertial coordinate frame. And column y is what they are actually representing, the inverse one actually. So with this is the inertial coordinate frame, projection of the unit vector of the inertial coordinate frame with uh, x-axis of the body coordinate frame, projection of the inertial coordinate frame with respect to the y-axis of the body coordinate frame, projection of the inertial coordinate frame with respect to the um, z-axis of the body coordinate frame. So that's important to know, and since it has tremendous application, so we should know about this geometrical interpretation. And then just before wrapping up on Euler angle, as you know, is extremely important for representing orientations. And before a class of programmers were took over the graphics and computer game designing part in robotics community, we also used Euler's angles. There are 12 Euler angles set. You can see Craig's book, Appendix B, and we have just taken three. Okay, we have studied three. What will be the composite rotation matrix, and just try to take one of them for uh, getting a solution. Okay, one of them is type 2, and this is the sequence of rotation, right? So this is the sequence of rotation that rotated about, say this is my coordinate frame, and first sequence is this one, right? Or this is equivalent to, as you know, this is equivalent to this sequence when all the operations are giving with respect to the one of the principal axis. Here operations are giving sometimes with respect to the principal axis, sometimes about body coordinate, some of the principal axis of the body coordinate frame, etc., etc. And how the sequence, how the composite rotation matrix can be obtained, as I told you in my earlier lecture, just put a unit matrix 3 cross 3 and then see if the operations are given with respect to some of the principal axis of the body coordinate frame, then pre-multiply in the same order. Okay, uh, and if the rotations are given with respect to the body coordinate frame, then post multiply this unit matrix I. Okay, and as you know, there are several sequence of operations which may lead to same composite rotation matrix. This is one of them, this is another, and there could be other also. So we are trying to understand, okay, that here all the since all the rotations are giving with reference to some of the principal axis of the inertial coordinate frame only. You see z, y, z. Then they have been, the sequence is like this. So all have been pre-multiplied, and why they are we deduced earlier. Okay, so now let us see that this is operation. You can also see this way also, but here let us see they're the same. So this is my coordinate frame xyz. Okay, and then about z first. So I am looking from here about z by an angle psi, and then it flipped from x1 y1 this position, and then with respect to y, so I am looking from here, and with respect to positive direction with respect to me, theta angle is rotated. So then the coordinate axes are flipped actually and took the position like this. So this is x1, x2, okay, and then y1 and y prime, y prime 2, they are the same because you are rotating about this axis, followed by, of course, a rotation of rotated z axis. So here, uh, looking from here, okay, these are the three operations which have been given, and as a result of that, you see this is a coordinate frame, and they are representing, say, a body. Okay, so as you know, with So the body will undergo several, with this three orientation, it will take some orientation. It will be kept in some orientation. And the description of which can be given by multiplying the three matrices. These are the three matrices. Now, so rotation about z, so 0 0 1 0 1, and these are the by phi, and then a rotation about y, and then rotation again about z. So these are the three individual matrices corresponding to this sequence, and then when multiplied you are getting this. So this is abbreviation which we are taking: sine theta equal to s theta to save space, and cos theta equal to c theta. So with that, we have got, this is our uh, composite rotation matrix, so-called. Okay. Now, let us see what is happening. Suppose now I have a orientation matrix which is given R11, R12, R13. This is 3 cross 3 matrix. Okay. And R21, R22, R23, then R31, R32, R33. So this is the rotation matrix, say B with respect to A, which is given, right? B with respect to A. And if you consider that this is a aircraft, and then this is the given, means with respect to aircraft is A. So B is the runway. So orientation of the runway B with respect to aircraft, say, is given. Now aircraft need to plan what will be theta phi psi, so that it can actually take that orientation. Okay, so this is equals to this equal sign. Okay, and now this is actually uh, this. Okay, now if theta not equal to 0, then you will get, I am just, I will tell you how you have got it, but it's very simple. Theta equals to 8 and 2 plus minus root over of r31 square plus r32 square, comma r33. Okay, so these are the elements which are given. Okay, and how you got this? You see, I have 9 elements here, I have 9 elements here, so I can generate 9 equations by equating the corresponding elements of the matrix, rotation matrix. For example, this one is equals to r11, this is equals to this c phi, cos theta, sin psi minus sin phi, cos psi. This is actually r12, like that. See, cos phi sin theta equals to r13. Okay, so I can equate. It's my choice. The objective is to uh, eliminate all other, keeping one unknown. These are all known because these are runways orientation. So this all is given to you, given to the aircraft. Okay, and then 8 and 2 this. So we can actually now we have got this solution. Now whenever theta is in between 0 degree and 180 degree, we always consider this positive sign of the square root and get the single solution. Okay, because these are all the solutions, right? So we are now constraining, say, theta between 0 and pi. So we'll take positive sign only, and we'll get uh, this as my solution. Now, what will happen if theta equal to 0 and pi? The solution of 2 will degenerate, problematic, and only sum of the difference of phi and psi, okay, can be computed. Okay, so one possible solution could be theta equal to 0, phi equal to 0, psi equals to 8 and 2 minus r12, r11. And when theta equal to 180 degree, now theta equals to 180 degree of pi, phi equal to 0, psi equals to this. So far so good, except this degeneration case. And believe me, this hardly happen in case of aircraft. If it is a passenger aircraft, it's very unlikely that the aircraft situation will be like this, or it will be completely like this. So the gimbal lock situation or degenerating situation will be rare. But of course, fighter plane which is maneuvering like this, so this could be the gimbal lock could be a reality. So gimbal lock is the inherent problem of Euler angle representation, right? So here you have seen the solutions are degenerating, and if I talk now with respect to robot now, okay, so you see what is this? This is my robot uh, gripper, right? And here three joint axes are intersecting. You see, 4, 5, and 6. Uh, this is 5, so this is actually Z is actually perpendicular to the board, Z5 perpendicular to the board, so it can rotate like this, okay. uh, that means like this, together with the housing. And then Z6 and Z4, they are, you see, parallel, means this is uh, Z4 and this is Z6, okay. So that's a problem, means in some situation that, for example, theta 5 equals to 0, this is the signature of, meanwhile, this is the drawing of the gripper and this is the gripper signature, which shows that this axis, they are perpendicular, Z5, Z4, Z5 is perpendicular to Z4 and Z6, okay. And they actually, it actually controls whether there will be gimbal lock or not, okay. uh, and this is of course Baxter robot. So I have given you two robot example, one uh, Puma, and another is redundant robot. Redundant robot is, it has 6 degrees of freedom. 3 are here, and other 3 are one here, another one out ground. 6 coordinate, 6 degrees of freedom it has, but it has 7 degrees of freedom. You see, 1, 2, 3, 4, 5, 6, 7, and these 3 actually are representing the gripper, and there could be some situation for which gimbal lock may arise when we try to describe orientation with respect to using Euler's representation. Okay, okay, and what happens if gimbal lock situation happens? It is dangerous for the gripper, because then theta 5 torque has to be infinitely large, because it has, first of all, it will lose 1 degrees of freedom. So this and this are same degrees of freedom. So it is constrained in that configuration. And that will happen when torque momentarily becomes extremely high to rotate this motor, okay, to take out from the gimbal lock situation. So that's are actually those are not good for the robot. So we need to avoid singular configuration, right? This is also called singularity when gimbal lock happens. So with this, I conclude that how Euler's angle can be used for describing orientation, how using Euler angle and A10 function, you can generate solution, okay, or plan a solution which will help my robot gripper or the aircraft to take a desirable pose uh, given which is familiar, which is coincident with the given orientation. Okay, so next we'll try to describe that why in robotics and in other field, in computer graphics, in your uh, in your mobile phone, the orientation nowadays is not described and calculated with the help of Euler's angle. Rather, quaternion is taking the place of Eulerian representation. So, in the next class, I'll try to introduce you with orientation representation using quaternion, and especially with programming is what quaternion has. It is very important to know about that tool. Okay, so those who are interested to know about this, please stay tuned in the next class. Till then, stay safe, have a nice day, goodbye.